Welcome, calculus students. Here we are with rational functions today. Rational functions are very much like polynomials, except that they're the ratio of two polynomial functions. Hence the word rational, ratio of two polynomials. Now, which polynomial is on the top and which is on the bottom makes a big difference as in terms of what's going on here. So when we look at the domain of this reciprocal function over here, fx is 1 over x. What's going on here? Well, what happens at x equals 0? At x equals 0, we find that we have division by 0, so that's undefined, and you get this vertical asymptote. There is a vertical asymptote, like this. We also see that this restricts the domain. X cannot equal 0. We also see there's going to be a corresponding restriction on the range, and it's something called a horizontal asymptote. Y cannot equal 0. Now, this x cannot equal 0, you can see from the equation itself. Set the denominator equal 0, you can find out where you've got undefined values. This y cannot equal 0 is a little trickier, and it has to do with looking at the graph and also some of the coefficients involved. So here's the formal definition of horizontal and vertical asymptotes. A vertical asymptote is something that, it's a vertical line, x equals a, that you get closer and closer to. As you approach x, like in this one, as you approach -1, you get division by 0, so you're going to approach the infinities. Here's an example of vertical asymptote where you approach the same infinity. That's part of the definition. You either approach positive or negative infinity as you get closer and closer to vertical asymptote. Part of the reason behind this is the double root here in the denominator. Now, y equals b is a horizontal asymptote is if as the y's approach b, then the x's approach infinity or negative infinity. So as x goes off to infinity or negative infinity, we're getting closer and closer to this horizontal line here, y equals 2. And we're going to see shortly that has to do with the ratio of the coefficients of the two polynomials, the one on the top and the one on the bottom. Here's a horizontal asymptote of y equals 0, because the bottom is growing much faster than the top. Okay? Same thing with this one. The bottom of x minus 1 squared is growing much faster than the top, so it's approaching 0. Now, for a rational function that is a ratio of two polynomials, as long as you got this fully reduced, then you get the vertical asymptotes by setting the bottom equal to 0. The horizontal asymptotes are a little trickier. If the degree on the top is less than the degree on the bottom, we saw some examples of that over here, then you just get a horizontal asymptote of y equals 0, the x-axis itself. If the degree on top is bigger than the degree on the bottom, then you don't get a horizontal asymptote because the top is growing faster than the bottom. When the degrees are equal, that's when we look at the ratio of the leading coefficients. That's what happened over here on 2x plus 1 over x plus 1. Same degree, they're both first degree, and so the horizontal asymptote was that y equals 2 over 1, or 2. Y equals 2 is the horizontal asymptote. Now, let's find some vertical and horizontal asymptotes here. First, on the first one, 2x squared over x squared minus 1. We'll define the vertical asymptotes. We set the denominator equal to 0. So set x squared minus 1 equal to 0. So we have x squared equals 1, so x equals plus or minus 1. We get two vertical asymptotes. Vertical asymptotes at x equals 1 and x equals -1. For horizontal asymptotes, since the degrees are the same, they're both second degree, the y-coordinate of the horizontal asymptote will be the ratio of the leading coefficients, 2 over 1, so we get 2. So y equals 2 is the horizontal asymptote. Let's see if that bears out in a sketch. And it does. Here's our y equals 2 is the horizontal asymptote. And we've got vertical asymptotes here at x equals 1 and at x equals -1. We'll have some more tips later on to see how you graph the rest of this. For instance, like we get a 0 here at x equals 0, it's a double root, and that's by bouncing off. Here's another example, x squared plus x minus 2 over x squared minus x minus 6. First, you want to factor it, x plus 2 times x minus 1, and the bottom is x plus 2 times x minus 3. So it actually becomes a much easier function. F of x equals x minus 1 over x minus 3. And so for vertical asymptotes, we just set the denominator equal to 0. So you get x minus 3 equals 0, so x equals 3. That's your vertical asymptote. For the horizontal asymptote, they're both first degree equations, so we can look at the ratio of the leading coefficients. So that's 1 over 1, so that's 1. So y equals 1. We've got a vertical asymptote and a horizontal asymptote. And those show up on the picture of the, let me call up GeoGebra here. Here we go. In GeoGebra, there's our horizontal asymptote, y equals 1. There's a vertical asymptote at x equals 3. But what you have to watch out for is this hole. This is, I put a as a point on this hyperbola. But notice what's going on here with this rational function. Right here at negative 2. Suddenly says undefined. Even though it's not a vertical asymptote, it's something that makes the top and the bottom equal to 0, and that creates something called a hole, and we have a hole here at negative 2 comma 0.06. So let's back up and look at that again in our notes. Take this picture. Why are we getting this strange hole here? Well, because at x equals 2, f of 2, if we look at the original function, not the one I reduced here, but f of 2 is equal to 4 times 1 over 4 times, I'm sorry, at negative 2. At x equals negative 2, we have, using this factored form over here, negative 2 plus 2 over negative 2 minus 1 over negative 2 plus 2 times negative 2 minus 3. And we end up getting 0 over 0. That's called indeterminate, and a very important idea when we get to our next chapter on limits. Suffice it to say, it's not defined, and we have to write an open circle there to show that there's a gap in the function there. Because in the original function, negative 2 will not work. Well, we can look at sort of, we'll call this our second function here, f happy face. Happy face because there are no problems with it. If we look at f happy face of negative 2, we get negative 2 minus 1 over negative 2 minus 3. We end up with negative 3 over negative 5, or 0.6. And so we get a hole at negative 2 comma 0.6 because negative 2 makes both the top and the bottom equal to 0. So just be careful of that. Now, here's a whole guideline of things to look for in rational functions. Simplify as much as possible. That means get rid of those things that might cause the holes. Plot the y-intercept and the x-intercept by setting the numerator equal to 0. Get the zeros by solving the equation of the denominator, because those give you the vertical asymptotes. We talked about horizontal asymptotes. This one, plot at least 1 point between and 1 point beyond each x-intercept and vertical asymptote. I think you can pretty much ignore this if you use the common sense approach of connecting your points and heading toward the right infinity. The y-intercept should usually help you get the idea of the flow. Now, this I've got available as a PDF on the Wikispace, this Calculus Rational Rainbow. It's the colors of the rainbow as a way to remember a lot of the different aspects of things you should be graphing. We haven't talked about some of these aspects yet, but I just want to refer you to this document. And here there's a lot more detail about the asymptotes that we just discussed. Let's practice doing a lot of problems here. I'm glad the book mentioned this technological pitfall too. Sometimes people graph, and it's not so much a problem in the 89s, but it might be on your 84s or your 86s and so forth, that you get some funky things like this where graphs a rational function makes sort of a connected vertical line here where the vertical asymptote should be. And kids get the wrong impression this is a connected graph. It's not. Or if you're in dot mode, you might think that the graph is actually separate points here, but it's just not connecting the dots with little vertical line segments of pixels to make it look more smoother. So watch out for those two modes when you're graphing. Sketching the graph of rational function. We have several examples I want to practice here, and let's look at a lot of the details involved with each. 3 over x minus 2 and state its domain. Well, the domain restriction is going to come from the denominator here. The denominator, x minus 2 cannot equal 0, so x cannot equal 2. So there's your domain. That's the domain, and here's the sketch. We put a vertical asymptote at x equals 2. Notice the difference between these two statements. Here I'm saying the domain restriction, all real numbers except 2. And here I'm describing the vertical asymptote at x equals 2. And we should put the y-axis back in here. Now, what else do we need for the graph? Well, we've got a horizontal asymptote at y equals, because we have a degree of 0 on the top and a degree of 1 on the bottom. The degree on the bottom is higher, so it's just y equals 0. The x-axis itself becomes the horizontal asymptote. And you can also get some more points. If you set x equal to 0, you get negative 3/2. That gives us the point right there. And then you can sketch through based on those points. It's going to switch infinities here because it's a single root in the vertical asymptote. Now this rational function is a little different. Sketch the graph of 2x minus 1 over x. Again, the domain restriction is going to be that x cannot equal 0, and that creates the vertical asymptotes as well. Vertical asymptote at x equals 0, like that. And let's get our x-axis back in there. And horizontal asymptote at y equals the ratio of leading coefficients, because this is first degree over first degree. Look at the ratio of leading coefficients, 2 over 1, and we get 2. So y equals 2 is the horizontal asymptote. Like that. And y equals 2. Now, the rational function's x over x squared minus x minus 2. How does this get so many asymptotes? Well, it's because the bottom factors, the x minus 2 times x plus 1. So we get a domain restriction of x cannot equal 2 and x cannot equal negative 1. And so we get vertical asymptotes at x equals 2 and x equals negative 1. Back at it. Now, what about the horizontal asymptote? Y equals the ratio of leading coefficients. Oh, hold it. This is first degree over second degree. So the bottom has higher degrees, so it's just going to be a horizontal asymptote of y equals 0. There's your horizontal asymptote. We can plot some other key points by just using your xy chart. If you set x equal to 0, you get 0. And that's pretty much soaks up both your x and y intercepts. Now, how could you do this without having to sketch a lot of the other points here and so forth? Well, I would try one point, like they did here at x equals 1. Put in 1, you get 1 all over 1 minus 1 minus 2, so that's negative 2. Or negative a half. So 1 goes to negative a half there. And that can get you started with the sketching, because you know you have to get closer and closer to that vertical asymptote. This is the only x-intercept, so you're never going to cross again. We switch infinities because this is a double root, this is a single root in the denominator at x equals 2. And we start getting closer and closer to the horizontal asymptote. In this direction, we don't bounce off because it was a single root in the numerator, so we pass through. You got to go closer to that vertical asymptote, and then you switch infinities. Now, here's one with a few things going on here. You might think, well, where are the two vertical asymptotes? Because we got this in the denominator. But if you look at the factoring, it's x minus 3 times x plus 3 over x minus 3 times x plus 1. These cancel out, so we simply get x plus 3 over x plus 1. That's f of x, but let's just call it the sort of the happy version of f of x with no little problems or issues in it. And that thing has a vertical asymptote at x equals -1, because that makes the denominator equal 0, so there's your -1 vertical asymptote. And a horizontal asymptote at the ratio of the leading coefficients. And we can either use these or the original ones too. 1 over 1 equals 1. So y equals 1 is the horizontal asymptote. What happens here, and what I want you to focus on, is this hole. This hole right here at x equals 3. Because 3 makes 0 on the top and on the bottom, so there's a hole there. How do we figure out how high to make the hole? Well, look at f of 3. In this case, instead of using the original function, we'll use the happy face function there. And that's 3 plus 3 over 3 plus 1, which is 6 over 4, or 3 halves. So there's your hole at 3, 1.5. And it looks about where it is on the graph there. And slant asymptotes now. These can be a little tricky. Essentially, when the degree of the top is 1 higher than the degree of the bottom, then you can get a slant asymptote. Because you go through long division on this, or you can use synthetic too. Let's support this with a little synthetic division. You would put -1 in the box, put down the coefficients, 1, -1, 0, zip, 1, -1, -2, 2, 2. And so that's how they got x minus 2 plus remainder 2 over the old divisor. So as x goes to infinity, this part gets more and more insignificant. You're just approaching y equals x minus 2. So that's how you can get a slant asymptote. You still get the traditional vertical asymptote by setting the denominator equal to 0. X plus 1 equals 0. X equals -1. So there's your vertical asymptote in there like that. And you also have a slant asymptote now. And some of the other key points on here you can get by finding the zeros. So let's take a look here. If we set x equal to 0, we get 0. So that's that point. If we set y equal to 0, though, set the numerator equal to 0, you get x times x minus 1 equals 0. So you get x equals 0 or x equals 1. So that's a source for another point there. You get another point here at 1, 0, and at 0, 0. And you're not going to cross the vertical asymptote. And you might say, well, how do I know it didn't go this way? Well, that would cross the slant asymptote, and we want to approach the slant asymptote, so it's going to go down this way. And switch infinities here. Now, let's sketch the graph of this. This is different than the other one, right? Yes. X squared minus x minus 2 over x minus 1. So we can go through, first, let's get this into its alternate form by dividing out. We suspect a slant asymptote because it's 1 degree higher than the bottom. So I'm going to put 1 in the box. 1, -1, -2, zip, 1, 1, 0, 0, 2. So I end up with x plus 2 over x minus 1 for the slant asymptote. That's what the function f of x equals. The slant asymptote is just this quotient right here. So the slant asymptote, SA, at y equals x. Still get a vertical asymptote at the normal spot x equals 1, because that's what makes the denominator equal to 0. And we can also look for roots at when the numerator equals 0. Setting the denominator equal to 0 gives us a vertical asymptote. Setting the numerator equal to 0 gives you the x-intercepts or roots. This factors x minus 2 times x plus 1. So we get x equals 2 or x equals -1. So let's try and work in everything we've done so far into a picture. Pause for a second. Let's see, we have roots here at -1 and +2. A slant asymptote at y equals x. A vertical asymptote at x equals 1. Do we get a y-intercept? Y-intercept of 2. If we set x equal to 0, we get a y-intercept of -2 over -1, which is 2, 0, 2. So this is all falling into place nicely. From here, I don't want to go down. Like that instead. And this switches infinities here. Turn off this way and this way. Let's see how we did vis-a-vis GeoGebra. Okay, we're looking pretty good because here's our approximate sketch, and here's the one from the book, and here's GeoGebra. Flange out.